So the next step after we've activated the carboxyl group, where we want the amide bond to form, is to couple it. So in our example, leucine will be the amino acid that we're coupling with. So the general scheme is that we're taking the alanine that's activated in the carboxyl group, and then we are reacting with the next amino acid. And the next amino acid, notice, will now form the amide bond, which is here. So this is the next amino acid, and because the carboxyl group is activated, the amino group of the next amino acid is able to come and react at this carbon and make this leave as a leaving group. All right, so here's the specific reaction of it. This is the leucine, and notice the leucine is not protected in the carboxyl group. We want the amine to be free to be able to do this chemistry, but the reason why the carboxyl group is not protected is because of the two, the carboxyl versus amine, the amine is the more nucleophilic center. So when you try to do this chemistry, the amine will win in attacking that activated carbonyl center. All right. So then you have made this bond in this step, and so here's the protecting group, and here's the alanine, and here's leucine, and you made a bond in between them. All right, so if your goal was to stop here, make a dipeptide and you're done, then all you have to do on the last step is to deprotect the protecting group. So notice the P is taken off in this general scheme. And then in this example, this protecting group happens to come off very easily with hydrogenation, but the basically the BOC and the FMOC group, they come off very easily with acid and water. So you'll see various conditions in deprotection step. The acid that they like to use is trifluoroacetic acid a lot of times, so you'll see that as the acid to deprotect. So notice at the very end then you have what you wanted, which is alanine with leucine dipeptide. Right? Now let's say though you want to make meganin and you want to keep making the 20 amino acid, then what you do then is you could keep going. And all you have to do then is to activate this. So go back to step 2. So throw in either the DCC or this chemical to make it into an anhydride at this carboxyl group. And then go back to number 3 where you throw in the next amino acid, which will couple it. And then you keep going on and on and on until you're done with the 21 amino acids, and then you deprotect, right? So this is really very simple scenario. Obviously for amino acids that have acidic or basic side chain, you have to do other things with it, but I just want you to be aware of the overall strategy and what is involved in each of the steps to make peptides. All right, so that's really what you would do in lab if you didn't have an automatic peptide synthesizer. Okay, so in 1984, a Nobel Prize was given to a scientist named Merrifield, who designed this. It's an automated solid phase peptide synthesis. And the difference is in here, you're using a polymer. Sorry, this is very faint. But the polymer part is sort of in gray, that's why it's faint. So you buy this resin, these polymer that has this functional group attached to the polymer. And what you do, if I blow it, you can see better. So what you do is you have an alcohol group coming off of this polymer, and what you do is then you link your carboxyl group of your amino acid. So you buy this amino acid in which the amino group is protected already, and then you activate the carboxylic acid with DCC, or diisopropylcarbodiamide, and you make an ester functional group here. So then this amino acid is now stuck onto this polymer, and then this amino group is free to do the coupling. So what you do then is, this is the step that deprotects the FMOC, so then you get the free amine, and then you take the next amino acid that has the amino group protected, you activate the carboxyl group of that, and then you do the coupling. And then after you do the coupling, you deprotect it with the same step, and then you just keep repeating it, and you keep making the chain long and long and long. So what you have to do in each of the steps after you make the coupling is you have to rinse everything else off and filter everything off, because what you want is attached to the bead. All right, everything else gets washed away. So there's no, like, if there's a side reaction or if anything else happened that's not attached to the bead, you're basically removing it by just simply rinsing it. That's why it's possible to do this automated synthesis. All right, so after you attach it, you rinse it. All the other stuff that's not attached gets removed, like the protecting group, and then the solvents that have the reagents in it, everything is removed, right? And then you add the next one, and then you do the same thing and same thing and same thing. At the very end, what you would do is you take it off the polymer, and you do that by treating with trifluoroacetic acid. And what that does is cleave that ester bond, and it releases the peptide that you synthesized. All right, so this is the way all the peptides are made now. It's not made by hand, if you will. This has tremendously simplified making of the peptides, and it allowed a lot of different research to be pursued, because it's easy now to make small peptides using this solid phase synthesis. All right, so at this point you should be able to do problems like 25.34a, 25.35, and you could even challenge yourself and be able to even make Meganin, you know, on the paper, obviously, using any of the methods that we went over. All right, so that concludes the lecture for the peptides sequencing and synthesis, and the next lecture will be on proteins.